Hello everyone, this is Priya Ahmadi, PhD in Mechanical Engineering. Today I'm going to just share you about the solar PV hydrogen production system using TRNSYS. So first of all, I'm just going to tell you to pull up the TRNSYS. As we practiced before, we need to just open a file here. Then if I just click on empty TRNSYS, then I'm just gonna open this screen. So a little bit information about the system. The system is composed of PV panels and of course a hydrogen production system, which in this case is going to be an electrolyzer. Then at the same time we need a compressor to compress the hydrogen up to 200 bar, and we need an storage to store and to keep the hydrogen at high pressure in that tank. So these are the main components that we need, but I will tell you step by step what other components we need in order to be able to simulate the system using TRNSYS software. So whenever we want to use TRNSYS software, first of all, we need to have the weather data. So I just go to weather data here. I use standard format. Then I go to TMY2. I will select type 15.2. Then if I select on that one, I will go to external files. Then I just click on the browse. Then here, on the location where I already installed TRNSYS, I have the weather folder. Then I select one of the places in United States. So as a case study here, let me go to, for example, Florida, Miami. I just select on this one, and this is just selected. Then what I need to have PV panel here, because I need to have something to produce electricity for me. Then if I go to electrical here, then all the way down to photovoltaic panels. So I have to advanced option and basic model. Then I just want to use basic model here, which is the type. Let me check it. So I just want to show you with no MPPT, because in other videos I just told you how to use this one. If you just go and watch the video that I already posted on my YouTube channel, then you will see. But here again, I'm just trying to have that basic model with no MPPT. Then I will tell you why and how. So for now, I'm just gonna just I'm just gonna select type 130 here and drag it here and drop it there. So in this case, what we need to do, we need to first click on type 103 here. As you can see, there are some variables here in the parameters, and of course I have some inputs, and I will get the output later on. But again, in another video I told you about all these parameters here, so we need to select those ones. So in this case I have the catalog. Then you can just watch that video that was already posted about PV for the performance curve, I mean I and V. Then I just told you how to just use all these data, then verify those. But to save time here, I just input the data here. Short circuit amp should be 9.23. Then the voltage from the catalog that I have is 38.3, and this one I leave it 25. The reference in the 1000. Then module voltage Vmax is 31.46, and here is maximum amp, which is 885, and ISC, which is here in this case based on the data that I have, is 0.047, and temperature coefficient VOC is negative 0.3409, and everything else looks okay. But here number of cell in series, I will change it to 60 according to the data I have from the reference. Then I need module area is 0.89. That is okay, but I can just change it to 1 meter square because most of them is 1 meter square. Then in series is 1 and in parallel is 30. So because I want to have more of these panels here. But again, what is important here is the load voltage, because I have used the no MPPT according to the IV curve that I already already told you in details. In this case, the catalog that I used, so around 30 volt is like the maximum performance of that one. Just let's leave it for 30. So for now, again here. This looks okay for now. Let me just move it a little bit up. Then I need to just connect the weather data to the panel. So let's see what we have. So dry bulb temperature, we link it to ambient temperature. Then beam radiation is here. Beam radiation for surface. Sky diffuse radiation is sky diffuse radiation for surface. Ground reflected diffuse radiation is ground reflected diffuse radiation here. Then array slope, I will just tell you in a moment. Incident angle of the beam is total angle of incidence for this one here. Load voltage, I already entered that, and this one I leave it there. So the question here is array voltage, what I need to do, since I'm trying to have it for the one of the cities in Florida. So we need to just check it and find the optimal angle for the installation of panel from the ground. So in this case, I already searched that and I found this slope. Here is array slope is around 28 degrees. So you can find that one. If you don't have that one, and if you just select with the weather data, it just counts it for 0. That's what we need to just manipulate it and enter it at the optimal value that we can find it from the net. So okay, let me just show you how much electricity that we can produce with this 60 of these panels in parallel. If I just find the plotter, online plotter with file with no units, let me just show you to have a better sense of what is the maximum voltage that I can produce using the system. So if I just array power here to the left axis, then in order to see the unit, if I click on that one, go to the output, array power, here array power, the first one is watt. So that's why I use the first one as watt. Then let me just start with from a 0 hour. 1 year is 8,760. So to save time, I just use it hour by hour. Then if I run that, then you will see that there should be a problem because we didn't check the units. So let me just stop that one. I already told you about all these steps. If I go to this one here, the parameters for the online plotter, you will see that the left axis minimum is 0. That is okay, but the right side, that should be like with the that size of panel, I will get around 9 kilowatt of electricity. Let's make it 9,000 watt because the unit, as I already told you, is watt. Then if I run it again, then sorry, that was 2, that was 90, so that should be 9,000. So if I just again click on that one, you will see that in the city Miami, in Florida, I can get around 8,000 in maximum time. But of course, I have, for example, here in January, I have something around 3 kilowatt and 4 kilowatts, so depending on the condition. And as you know, that Florida is one of the places in the United States with a higher solar radiation. That's one of the intention. I just selected that location, but we can just select any other location as you wish. But again, what else we need for this system? Of course, we need to go to the hydrogen. Where is the hydrogen system here? The hydrogen system. I need to use an electrolyzer here. So the TRNSYS just has alkaline that does not have any PEM and other type of electrolyzer. But as you can see, there are 3 types of electrolyzers. So then I will tell you momentarily that what the differences are. So for example, some of them, they consider the temperature of the electrolyzer as a constant. Another one is not constant. Another one has the cooling system. But for now, I just use type 160A here. Then what else I need? For sure, I need a compressor here because I need to compress the hydrogen. Here, I just use a compressor here. Then again here, so for sure, I need to have a compressed gas storage because I need to store that one. So compressed gas storage, if I select on that one, I have for hydrogen. Then I have 2 options: ideal gas or real gas. So the difference between ideal gas and real gas, you know about that one. The ideal gas is the PV is equal to nRT. The rule is applied, but like for real gas, we need to consider that compressibility factor because we are dealing with the high pressure, as you know. So since we are not going to just do all those formulas, so in the real gas, most formula is like those van der Waals equation of a state. They use that equation. So for sure, I'm just going to use the better and more accurate one. That's why I use this hydrogen tank here. But again, one of the things that is really important here is that we need to have a controller here. Because what the problem is, at night we do not have that solar radiation, solar power, or what will happen, we need to just shut down the electrolyzer, which makes the electrolyzer to be degraded. That's what we need to have an electrolyzer. So that's why the controller, sorry. That's why if I just select on hydrogen system, you will see that controllers. If I click on that one, you will see 2 controllers. One is for electrolyzer, another one is for master control. So the master control, I will tell you in other videos, because whenever we need to have another battery, diesel engines, and those backup power for the system, the bigger systems, then we need to have the master controller. But for now, what I need to do is just use the electrolyzer and use the this controller. So since we are dealing with the solar energy system that fluctuates, I just use variable power mode here. Then again, this looks like I'm already done, but not. Those who know about the basic of electrochemistry of fuel cell and electrolyzers, they know that electrolyzers work based on the current density. So like the one that we know from the idea is we provide the electricity to the electrolyzer, anode and cathode, then we can produce hydrogen and oxygen gases, then we can store that. But in reality, if you go to electrochemical formulas that I have it here, this is for the electrolyzer, that you can see we have several losses, V naught, which is represented by the TRNSYS equation, the maximum voltage that we have, and activation overpotential for anode and cathode, and ohmic overpotential. And at the same time, we might have at higher current density, we might have the concentration, and for sure they are gonna change this equation at the same time. So that's what all these overpotentials are a function of current density. Then with those current density or current, in a better way, current, then we can find the voltage. Once I have that voltage, I multiply that V multiplied by I, that gives me that W dot, the electricity that I need. So that's what I need to have a component here to change the electricity from the PV panel to the amp, to the current. So in this case, then in this case, how I can find it, I go to electrical. Let me check the power conditioning. This is power output. Power output is noun. If I go to this one here, power, because I have the power input. Power input is noun. Because I have the power, then I need to get the current. So that's what I select this type as well. So for now, I think I have selected all that I wanted. Then I need to just use all these things here to come up with the system modeling. Okay, again, so we have all the components here. Just let me rearrange them somewhere here, and this one before this. Okay, so first, this is the controller that I told you, because if I just click on the controller, you will see the electrolyzer mode. If I click on the mode, you will see power mode, one variable power and fixed power. So since it is variable power, because we are dealing with the PV panel, which has the fluctuation. This is SOC limit and SOC upper limit. This is for the tank. Between 0.7 and 0.9. So this is really important. Idle power. As I told you, the electrolyzer should be working at the minimum power, because what will happen if we just turn them on and shut them down, there would be a lot of damage or electrolyzer degradation on that. So the question here is how to select this idle power. So it means that whenever the PV panel is not available, we need to provide that minimum voltage for that. So according to my experience, between 10 or 20% of the average PV panel would be fine for that. As you remember that we had the PV panel W dot, we had around 6 kilowatt or between 2 or 3. So in the minimum power to the 8K from the city of Miami in Florida, we get that electricity from our PV panel. So let's say that on average we have 5,000 watt of that. So 10% or 20% of that would be something around 500 or 600 or 700. So let me just for now change it for 600 minimum power. Then if I click on the input, we will see that we have the tank SOFC with 20% and power to the electrolyzer that I will tell you later on about that one to see what that would be. So again, I just selected all of those. As you can see here, all the parameters here, and you can see about all these details. So that is 600. Let's make it 800 for now to be on the safe side. Then that's really important. Okay, so here, so first, the electricity provided by the PV panel should be connected to this controller. Let's do so. If I click on that one, so voltage, array current, array power, so that should be array power should be to the power to the electrolyzer, as you can see here, to the electrolyzer with this one here. Then, so tank SOC, I will get it from the tank. Then for now, that is okay for this type. Let me just move it a little bit here. Here is fine. If I click on that one, if I move it here, okay. So no, not here. Let me just move it up a little bit to. Okay, so here. Then again, what we need to do, we need to see about other options that we have. So let's just click on the electrolyzer for now. Just leave everything alone here. Let's get back to the electrolyzer where this is really important. Okay, so electrolyzer parameters. Temperature mode, electrode area, so this is 0.25 meters square, which is the high. That could be all the electrolyzers, all the cell and in series and parallel, and this is the one that we have electrode. If I click on that one, the more area of one electrode here, then number of cell in series, I have 21 here. Let's change it for now for 20. Then number of stack in parallel. Just that's what is really important is the number of the cell multiplied by the total area that we have, that we can just do the calculation here in this study. And here there is another not a problem, but we need to make sure that it's really important. This is a maximum allowable current density, as you can see here. So at higher current density, the concentration loss in electrolyzer and fuel cells are really significant. But here the problem here in TRNSYS, they have these parameters up to 1,000, as you can see here. But for now, let me just plug 1,000, because for more than that one, because most of the electrolyzers, they are working in the range to have the best performance in the order of 500-600 milliamp per centimeter square, and the maximum allowable operating temperature is 80. And these are just like some of the inputs for the fuel cell. I will just leave them alone in this case. Then I will get back to those ones. So if I look at the inputs, so I will see that I have all these options. So the question here is, according to just the functions and equations were written in this type, so we assume that the pressure of the outlet condition of this electrolyzer is being produced at 7 bar, and the electrolyzer operating temperature, let's make it 70. But again, this is really important here. What about the area? And how many cells do we need to find in series and in parallel? Okay, so this is really important. Okay, what we need to do, as you can see here, this is really important for us. We need to make sure. How much power do we have on average? Let's say at maximum we produce the electricity from the PV panel around 8,000, but minimum we have 2,000. So let's say that on average I will get something around 4,000. So this 4,000 watt. Okay. So if I can show you here, this is really interesting. Let me just do the pen here, pointer and pen. Okay, so here, let's say that, as I told you, in electrolyzer, I have I, which is current density. Then with this I can find all V nearness, V activation, V ohmic, and over potential of concentration. So then, when I have this I, if I multiply by that V, which is the summation of all these over potentials, I will get the voltage, operating voltage of a single cell, or if I just make them in parallels and in series, I will find that. Then if I multiply that I, the capital I, by V, I will get this W work, which is coming from the PV panel in this case. So as you can see here, from the IV curve, this is called polarization curve. This is V and this is I, current density. Then, as you remember from the graph, then they start from here, from somewhere 1 point something, then all the way down to maybe 2 volt here, or more. Then most of the electrolyzer are working in this area, so where the current density is something between 500 or 500 milliamp over centimeter square, or 600 or less than maximum 1,000 milliamp over centimeter square. So in this current, so the voltage is something around 1.8. So that's what one cell gives me this this number. So in this case, I can find the area, the relevant area for one single cell. So in this case, since I had 20 of those, so that W, which is, let's say that 5,000 of watt, is equal to number of those 20 I times V, right? So in this case, V, I told you it is something around 1.8. Then if I do the multiplication and do the simplification here, 5,000 watt divided by 20 of them in parallel and divided by 1.8, then I will get that I, which is amp in this case, but according to that, we need to find that area. So if I do all this calculation, what I will get the area which is represented to that area. It would be something around the proper area for this fuel cell to be working in that area is something around 0. Maybe the area would be something around 0.03 meters square, not 0.25 meters square. So in this case, I have a good electrolyzer to come up with an idea. So this is how we select that. So in this case, if I just use more PV panel, I used to increase this area as well, because I will increase that number. So that is the reason I just use all these calculations. Let's keep this one, get back to the TRNSYS. So in this case, I will change this number to 0.3 meters square and change them to 20, and everything else looks fine here. So that's it. So let's look at the inputs. What I need the electrolyzer control signals and mass flow, electrolyzer operating temperature. So here. Okay, that is interesting here that I just selected that one. Let's click the controller from controller to the that is important. Okay, let me just, I didn't tell you here. So here, as I told you before that, so first I need to give the power to this inverter to change the W, the electricity, to the current, then provide that current to the electrolyzer, as you can see here. So from the power here, if I select to this inverter here, look, power set point and electrolyzer control. So power set point should be to the input voltage. Oops, wait, that didn't accept that. So I already have that line. So I need to just use that again. Here, let me just select that. Power input to input power. That is okay. So I just use that one. Then here in this case, I will select the current to the electrolyzer here. Look, output current to electrolyzer current. So this is just asking about the units, just making sure the units are consistent. This is amp, so that is okay. I just click that one. So at least in this case, according to the formula that I have, so the electricity W dot watt is changing to current using these inverters here. But again, if I click on this inverter, let me tell you something. So there are some inputs and outputs. So nominal power, this is too much for this. So this inverter is being used for that PV panel with the maximum power of 8,000, right? So that's why we need to make sure that that is really important. So let's change it to 10,000, right? Yeah, we have 8,000. So let's say 10,000, because otherwise we will have a lot of loss here. So then I will change another one later on. So in this case, I have that current to that one again. So, but again, this is important to consider the voltage of the electrolyzer to this one here. So how? I told you. So how this modeling is being calculated here. So one current density is provided to this electrolyzer. According to that current density, the voltage is being calculated. The multiplication of those ones should be the W, the watt. Then we need to provide it for that one. This try and error keeps repeating in order to convert that equation. So in this case, what I need to do, I need to connect this electrolyzer to this one here, electrolyzer. So electrolyzer voltage should be the output voltage of this inverter. So the output voltage of this inverter is somehow the input in the electrolyzer. So this is really, really important that we need to do this one, because using this method, V and I could be converged. So what else I have here? The control signal should be okay here. For the sake of simplicity, let me just finish the electrolyzer here. So off and on switch. Let me change the on. So let me just change it 1 to be just on. Then it gets the signal from the controller to see when we need to just shut it down. So in this case, what I need to do, I need to just connect this one to the compressor here. Which one? To the compressor, just the hydrogen production rate. So hydrogen production rate to voltage flow rate of the gas entering into the compressor here. Then nothing else I need from here. I need to just move it a little bit up. Then again here, I need to have control signal of the tank. Look at here, look at the input of that one, tank SOC. Then let me just connect that one to this tank SOC, which is the pressure level of the tank SOC. Then here from the compressor output of the compressor should go to the tank. So hydrogen, where is that? Volumetric output flow should be gas entering the tank. Okay, so this is okay for now. Then what else I need to have here? So from the controller to the electrolyzer, let me see what we have. So electrolyzer control signal to the electrolyzer control signal here. Okay, so everything looks fine, but there is a problem here. If I click on the tank, so in this case, since just we want to have the tank to be just stored here, as you can see here, if I click on the hydrogen tank, I will have some parameters. So the parameters is pressure mode is 2. If I click that one, ideal gas is 1, real gas is 2. I already talked about that one. Maximum pressure, as you can see, this is 200 bar. So this is the limit for TRNSYS. If you want to do the transient simulation for hydrogen refueling station, where we have 350 bar and 700 bar, we need to develop our own code here. But again, tank volume, so this is really important. So for this size of electrolyzer and the PV panel that I have, so 1 cubic meter is fine. Otherwise, you cannot fulfill the lower limit of the tank and higher limit of the tank. So you need to make sure you have the numbers in your mind. So with this maximum 8 kilowatt of electricity, so 1 cubic meter would be fine. But again, this is another thing which is important. So in this case we do not have the fuel cell to consume hydrogen. What we need to do, we need to calculate that one to see how much we can get from that. Then in this case we need to do the calculation, which is really important, to see how much I need to have it for the exit condition. What will happen, because if it is 5, then we have more hydrogen getting out of the tank, and I cannot just reach the level of the tank and to control the control signal for this type 100. So if I have less than that, so of course I'm just going to keep hydrogen in the tank, then I cannot use it again. So the question here is how much that would be for us to calculate. Let me show you with this electricity, how much hydrogen I can get. Then I will just consider some part of that for this equation as well. Let's get back to the calculation here. Okay, let's move to the pointer here. Okay, so we have on average around something, oops, why I cannot write it here? Oops, there's a problem with this. Okay. Oh, okay. So here, let's say that if you remember, that was the electricity production during a year. This W double in watt. So if you remember, there was something like the graph like this, like this. In May I made that one around 8,000, but for sure we have like some numbers over there. Let's assume that we have on average 4,000 watts of electricity using PV panels. But again, for the electrolyzer, to see how much hydrogen I can produce, I know the efficiency of the electrolyzer, which is equal to the amount of hydrogen I can produce, hydrogen production, divided by, let me change the color here, black is better, color, let's change to black. So here, hydrogen production divided by amount of electricity that I will get. So the amount of electricity is mass flow rate of hydrogen times heating value of the hydrogen, then divided by W dot. So most of the electrolyzer from the company, if you just go and search them, you will see something around 65%. So in this case, m dot hydrogen is equal to efficiency of the electrolyzer multiplied by W dot times W dot divided by heating value of hydrogen. So in this case, efficiency is 0.65 times the average is 4,000 watt divided by HV, heating value of hydrogen, which is 140,000 kilojoule per kilogram, right? Then here we need to do like some simplification. So I just cancel this one with 2 of those. Then I will get 65 times 40. Instead of watt, I write joule per second. Then, so this is 65 divided by 140,000 kilojoule per kilogram. If I move this kilogram up, I will have kilogram per second. So I will just, delete this one as well. So I can cancel this joule with that. Then I will have m dot of hydrogen, which is equal to 65 times 40 over 140,000. I have the unit of K here. I have kilogram per second as well there. Then if I cancel this one by that, I will have 65 times 4 divided by 140,000, and I have K here, kilogram per second. So let me just do the calculation here for you to see how much that is. Then we will get back to you here. So I'm just using my calculator here to check the numbers. Here is 65 times 4, which is 260. 260 divided by 140,000. This is the number 0. This is the number 0.0185 times 10 to the power of negative 3 because of that one, kilogram per second. But the one that we want is cubic meter, kilogram per hour or cubic meter per hour. So if I want to change that, the 1 second is 360, 1 over 360. So this is going to be 0.0185 times 10 to the power of negative 3 times 360 kilogram per hour. So this number would be, I will show you in a moment. So that number 1857 times 360 3600 divided by 1000, that would be 0.06. So that would be, if everything is correct, that would be 0.06 kilogram per hour. But again, we need to change it to use the density to change it kilogram to cubic meter. So the question here is 0.06, I think, 0.06 kilogram of hydrogen per hour. I need to change it to cubic meter per hour because that was the unit which was in TRNSYS here. Let me show you here. If I just click on that one here, to the output, volumetric hydrogen dumped is cubic meter per hour. So that's why we need to use the density of hydrogen in order to find that. So the density of hydrogen, I need to find it in this case. So in some cases they find it at atmospheric pressure, but here since we have at 7 bar, so this is up to you. Let me just change the color here. Then I need to find the density of hydrogen to change this kilogram to cubic meter. If I do so, then I will get, if I select the number for the hydrogen leaving the system, in this case, something around maybe 0.2, that would be fine for me, because let's say that I have the hydrogen tank here. This is the tank, hydrogen tank. Okay, so the limit for the hydrogen tank was 0.4. As you can see here, 0.4, 0.4. This is the minimum one, but the signal was from 0.7 and 0.9 according to that one that we have, initial pressure level. Let me show you this one here. As you can just click on this one here to the input. Your initial pressure level is 0.4. Then parameters of that one for the hydrogen tank was in the controller here, because we had it here. Look, lower SOC is 0.7, 0.9. So it means that the electrolyzer just working between these pressure levels. So it means that if I have, again, I need to change the color here. Let me just change the color. Whenever I just move to another slide, that just automatically change the color. So that's what I need to come back here and redo all the process here. So it means that the pressure level is here. We start from here. So if we have less than 0.9, we use the electricity from either a PV panel or the controller here to store hydrogen from here all the way here. If we have more here, then there is a control signals on that to shut down the controller. Then here we just consume the hydrogen here. So if we go less than that, again we do not use the hydrogen. We just store hydrogen here. So we will see that when we get the results. So let me again come here to correct this one here. So input should be, look here, this is really it is too big. This number is too big for this case. So that should be 0.2. I will show you. So I think everything looks fine here. Let me just run the program, then you will see what will happen. So here, let me just delete this one here. What I want to show you is the pressure level for the gas is really important. So here is the pressure level of the tank. So pressure level to the left axis, so you know that the pressure level should be something between 0 and 1. So 0 and 1, left axis 0, this is for that PV panel. If I change it to 1, then everything looks fine. If I go to the special call left axis, let's say tank pressure level, tank pressure level for now, then change everything here. This is for 1 year, so hopefully we will get the results. Okay, so here that is perfect. So it says that The initial pressure is just starting from 0.4. The initial tank pressure, it just increases up to 0.9. When it reached that point, the pressure level, 90% of the tank is filled with hydrogen. Then what I need to do, I need to just consume that, but like using the tank. Then when it reaches, look at here, when it reaches to that number 70, look at here, look, this is let me just show you that number. It should be 70. Like, look, this is 70. When it reaches to the 70, then so it again gets the electricity from the grid all the way down here. So let me tell you something. Let's see what will happen if I change this one here, the volumetric rate of the hydrogen gas existing and leaving the system. If I change it from 0.2 cubic meter per hour to 0.4, let's again see the result. Let's see what will happen. Look, so that is not converged. So it means that this system does not have the ability to produce that much hydrogen. So that is really, really important for you to do the calculation. But if I just change this to 0.3, let's say maybe initial pressure is low for some, okay. So, but again, let me just finish that one here. So here, look at here. So it says that, so at the beginning of the process, the hydrogen tank was low, less than 0.40%. That's what we have that fluctuation. But again, it just increases at the same time. Then we have all these ones here. Then what else we can have here? So this is really important. We can have those graphs here, the hydrogen production rate. Let me show you this one here. Because we need it. If I just move it a little bit up, then from the compressor hydrogen production rate, if I change the volumetric flow rate to the right axis here, then if I just change the unit for the right axis, 1,000 is too much. Let's make it 5 cubic meter at the maximum size. Then again, if I run that, yeah, 5 was too much, so let me just change it to maybe 2 cubic meter. Then we will see the results here. Okay, as you can see here, this is the hydrogen production rate, 1.2 cubic meter per hour. But again, there are several problems here because this is not an advanced model. Look, what will happen here? Why do we have these numbers here? And what are those numbers? Look. This is exactly that ideal power, 0.16. So that is the minimum power that I told you in this controller, ideal power, 800 watt. So that means that at night, I need to have that much electricity. But again, as you can see here, we have some irrelevant numbers here. So why? Because this system should be working with another controller, with a battery pack, to smooth this electrolyzer here. So this is one of the simplest case for hydrogen production with PV panel. So today I just tried to show you some of the challenges we faced in the modeling of the hydrogen energy system. So of course you can draw, you can play with all those numbers, but make sure that this is not a perfect simulation. This is just for beginning of the system. I have thus modeled other sophisticated systems where we have battery, and at the same time, what if the output hydrogen leaving the hydrogen tank is not constant? For example, you are using a fuel cell at the same time dynamically using that hydrogen. So that's what, in several publications and several studies, we have all these systems. But at least we know how to model it, we know how to control the signal, we know how to come up with the membrane area for all of these systems. Then we can have the simulation. So here I'm just gonna stop the video. Hope you enjoyed from this TRNSYS simulation for hydrogen production systems. I will get back to you with the advanced simulation for hydrogen production. So thank you very much, and all the best, and enjoy your time.